Hello everyone, I'm Zeki and I'm going to present our work titled Agential AI for Integrated Continual Learning, Deliberative Behavior, and Comprehensible Models. In this work, we present the initial design of a system that is composed of three main components. First, a modeling framework that is capable of inherently learning continually without destroying past knowledge and generating a structured representation of the environment that it learns. Second, a planner that uses the learned model in order to generate goal-directed action proposals for the agent. And third, a behavior encapsulation mechanism that encapsulates different action networks that are generated by the planner. We only give a brief overview of these components. The full paper includes details and the full design of each of these components. So the first component of our system, the modeling framework, which we call modelleyen, is formed upon a principle of local variation and selection, as commonly observed in biological systems. This process reflects as the formation of exhaustive connections to an event that is desired to be explained in a given time step into all the possible alternative explanations for the event observed at this time step. These alternative explanations are then refined based on future observations, and then this process is continued for negative conditions which act as suppressors for this event to be explained as well. This process can be continued further upstream arbitrary number of levels in order to represent arbitrary disk functions over discrete variables. To give an illustrating example, a simplified one, suppose that you want to predict the circumstances in which a given prey animal is going to start escaping or running. Suppose that in the first observation, you see that the prey animal runs in a rainy weather and in the presence of another predator animal. Then you are going to form a connection saying that rain and the predator animal, both or alternatively, both of them can act as an explanation for the running of a prey. In a future observation, you may see that the prey animal does not run in the presence of a rainy weather. So you're going to refine that, and the presence of the predator is going to remain as the only explanation for the running of the prey animal. In an even further observation, you may see that the prey animal does not run in the presence of a predator if there's a protection for that animal, for example, humans with weapons. So the presence of the protection is going to be a negative conditioner for the running of the prey animal. You can continue this process upstream depending on the circumstances that you are modeling, so that you can model an arbitrary function that explains the running of a prey animal. Our planner approach is quite straightforward. It only operates by starting from the goal state and opening up the predecessors of a given node until it reaches the current observations, thereby connecting the current observations to the goals and finally proposing an immediate action based on this open pathway. Our behavior encapsulation mechanism takes different action networks, alternative action pathways from the planner and finds the commonality between them, encapsulating the details into edges and representing as nodes the common indispensable parts of these action networks, hence representing sort of a sub-policy between the given current state and the goal state. We verify our design in a simple finite state machine environment that models different aspects of learning. It has three different subtypes, which represent alternative connections, alternative transitions, and are designed for testing for continual learning performance. The details of this environment are also in the paper. In our results, we see that our modeling framework can properly learn an environment model, and the planner can generate good actions based on this environment model. We also see continual learning without destroying past knowledge, as evident by the preservation of the performance of the agent in past environments, even after it has been exposed to additional environment subtypes, hence not forgetting the previous examples, the previous environment subtypes. Our behavior encapsulation mechanism can also successfully encapsulate a complex action network into a simpler one, encapsulating the details into encapsulated edges as present by bold connections in the figure below, and keeping only the necessary information at the higher level. To conclude, we described the early design of a framework that addresses four common limitations in the machine learning systems, especially in agential systems. An ongoing future work of this work applies this approach to observation spaces that can be represented as networks in order to make it more generally applicable into more complex observations. Thank you for listening.